Okay, so I want to start today's lesson by taking up some of the homework that you guys had for the past class. It's on electrochemical cells. First example, show a diagram and half-cell calculations for an electrochemical cell with hydrochloric acid, lead nitrate solution, lead solid, and potassium bromide in the salt bridge. And then write what you expect to see in your diagram. So we first start by listing all the substances present. So as you know, hydrochloric acid will make hydrogen ions, right, which are essentially hydronium, but we can represent them by H+. It will make chloride ions. The lead nitrate solution will produce lead 2 positive ions. It will produce nitrate ions. We have lead solid. Okay, and the potassium bromide is in our salt bridge, so we're not going to list it here because that's going to be in our in the salt bridge, and that will have the ions migrating. Okay, the other thing that's present here is water. Okay, so we're going to write that down as well. Once we have the substances present, we have to look for what is our strongest oxidizing agent and what is our strongest reducing agent. So for that, we're going to have to go to our text, or rather the sheet that you have of the reduction half reactions, and pick out your strongest oxidizing agent and your strongest reducing agent. So you start at the top left for your strongest oxidizing agent, you go down until you find something, and your strongest reducing agent. So if we go down the top left to find our strongest oxidizing agent, what we do is we will probably find that our H+ is going to be our strongest oxidizing agent. And now I know you might think, oh yeah, but I saw this one with H+ and NO3-, so wouldn't those two together be your strongest oxidizing agent? Well, the H+ and the NO3 are in two separate solutions, so the H+ and the NO3 will be in two different half cells. So the H+ and the NO3, they're not mixed together, right? So what we have as our strongest oxidizing agent is just the H+. And then if we look for our strongest reducing agent, starting from the bottom right and then going up, we find that lead solid is our strongest reducing agent. Okay, so those are the two things that will be involved in the half reactions. Okay, so we continue by drawing out our diagram. And so we will draw the first half cell right here. It's in one beaker. And then we have our other half cell here, and that's in our other beaker there. Okay. Now, in one of the solutions, we are going to have our HCl solution. So I'm just going to arbitrarily say that in here we have our right here we have our HCl aqueous solution. Okay, so in here we have our HCl aqueous solution, which means that we have H+ ions and we have Cl ions present in our solution. In the next one, we have lead 2 positive ions and we have nitrate ions in solution, right? Okay, well, where is this? But we said that this is our strongest reducing agent, so where is that going to be? Well, that's actually going to be one of our electrodes, and that's going to be this one right here. Okay, and this one right here is going to be our lead electrode. Okay, what are we going to use though for the electrode over here? We can't put the lead over here because then the lead will react with the acid and we're going to have a reaction in this half cell. And we don't want that. Remember, we want the reaction to go from one half cell to the other. We don't want the reaction happening within the half cell itself. So what electrode could I use to provide a surface where the H+ can react? If we flip to the previous page, it says, note, sometimes an inert electrode is used, carbon or platinum, and when we say carbon, we mean graphite. Okay, we don't mean diamond, we mean graphite, because recall that graphite is the only one that can conduct electricity. It has those delocalized electrons that allows it to conduct electricity. So we need a graphite electrode, which only provides the surface on which oxidation or reduction takes place. This is usually the case for non-metal oxidizing and or reducing agents. So this gives us a clue. We might have to use either a carbon graphite or a platinum electrode. And in this case, because we don't want to put the lead in this half cell, otherwise it causes a reaction here, what we're going to do is this electrode here is going to be made of graphite. Okay, so this is going to be our graphite electrode. And again, this right here, this electrode here, that's not going to react. It's just going to provide a surface for the H+ to react. Next I'm going to do is I'm going to draw my salt bridge right here. This is my salt bridge. Okay, I apologize. I know that does not look good, but and in my salt bridge I'm going to have my potassium bromide solution. Okay, so I'm going to have potassium ions here, and I'm going to have bromide ions here as well. Okay, because remember that when potassium bromide is in solution, it dissociates into potassium ions and bromide ions. Okay, and then what we're going to do is we're going to have, an electrical wire, and we'll put a voltmeter here. Right, that's the symbol for a voltmeter to measure the voltage between the voltage difference between the two half cells. Okay. So now that I've done my diagram here, what I'm going to do here is I'm going to write my half reduction reaction. And my half reduction reaction is going to be as follows. So I'm writing my half reduction, that's my 2H+ aqueous plus 2 electrons, okay, equilibrium arrow, forms H2 gas. And remember, I'm going to write my E0 value there, and that right there is equal to 0.00 volts, right? And remember, this is the hydrogen half cell. That's our, that is our standard. That's our reference point. So we've selected that as being our 0 volts, and everything is, remember, relative to this half cell, or this half reaction. Okay. Now I'm going to do my half oxidation reaction. Okay. And that is lead solid is going to give up 2 electrons to become lead 2 positive. So 2 electrons. Okay. And I'm going to write my E0 value there. And if you look it up on your sheet, it says negative 0.13, but that's for the reduction. So we got to flip it and we got to say 0.13 positive, right? And so we're going to add these 2 reactions. And as you can see, this is 2 electrons and that is 2 electrons. So I don't need to do any multiplications here. So I can simply add them, and I'm going to get 2H+ aqueous, okay, plus Pb, and then H2 gas, and lead ions. Okay. And we see that the difference here, the E net, is equal to positive 0.13 volts. That means that this is spontaneous. So this is an electrochemical cell that's going to produce a spontaneous voltage, right? Okay, so what's happening in this cell? Well, as we can see here in the oxidation, we have lead becoming lead 2 positive ions, right? So this one right here, this is going to be oxidizing to give off 2 electrons, and this is going to be forming lead ions. And if this lead solid is forming lead ions, well then this electrode is going to corrode over time, or corrode or dissolve over time. Now, it gave up those 2 electrons as we see here. Where are those electrons going? Well, those electrons are going here. They're going across the wire. And the electrons are going into this electrode right here. And what is picking up those electrons? Well, we see that the hydrogen is picking up those electrons. So these hydrogen ions that were in the hydrochloric acid solution, they're going to go onto this electrode, they're going to pick up those electrons, and they're going to come off as, oh, we have it right there, H2 gas, okay? And so what does that mean? Well, if it's making H2 gas, then we're actually going to see bubbles come off of here, okay? So we're going to see some bubbles come off of here. All right. We're also going to see some ion migration. So if the positives are reacting to form a neutral substance, then the positive ions here are going to migrate into this half cell. We will also see lead ions from this solution. They're also going to want to migrate up through here into this half cell as well. Okay. Now, again, if these are forming positive charges in this half cell, well then that's going to attract the negatives here. And the negatives are going to go into this half cell. This also means that the chlorides here will also be attracted to this half cell, so they're also going to travel through the salt bridge as well. So I still need to identify the anode and the cathode. And remember, I'm gonna think anox red cat, so anode oxidation. So oxidation is the loss of electrons. So that means this right here, that's my oxidation. Okay, that's this electrode. So this electrode is my anode. Okay, this is my negative. Okay. Red cat, so reduction happens at the cathode. So that means that this one right here is my, that's where reduction takes place. So sorry, I'm just going to write, this is my cathode right here, and that's positive. Okay, so that's my cathode. This is my anode. Okay. Now I'm going to put in my cell notation. Okay, so my cell notation is my anode, one line, because it is submerged in a lead nitrate solution. And then this here represents the physical separation. And then I'm going to put my other solution here, which is my HCl aqueous, or my hydrochloric acid. And then a solid line. And then a carbon graphite electrode, right? And that's my cathode. So this is my anode. This is my cathode. Okay. And this is my cell notation there. What are the observations that I'm going to see? Okay, so the observations I'm going to see is at the cathode, what will I see? Well, my H pluses are going onto the graphite electrode to pick up those electrons, and they're forming H2 gas. So I'm going to see bubbles forming. Okay, and those bubbles are going to be the H2 gas that's forming at the cathode. At the anode, what did I say was going to happen? Oh, well, my lead electrode is going to be dissolving over time because my electrode is undergoing an oxidation reaction. So I'm going to have my lead electrode, my lead electrode is going to corrode. Okay. I should also consult with the ion chart and the color chart, and I should see, in fact, that none of these ions have any specific color to them. The lead is colorless and the nitrate is colorless, and acid is colorless as well, so I'm not going to see any color changes. So this is essentially what I should be seeing here. I'm going to see bubbles forming at the cathode, and at the anode I'll see the lead electrode corrode over time, right? And the cell gets used up when the lead electrode completely is used up here as well, or the acid, there's no more acid, okay, and then the electrons will not transfer anymore.